When an organic molecule has carbon that has 4 different things attached to it, there are 2 ways that those 4 things can be arranged. And they may be mirror images, but they can't be superimposed. They are truly different. Let me write the mirror image. One way to write the mirror image is just literally reflect the atoms into a hypothetical mirror plane. And I've put an orange rectangle in here to represent the mirror that these various groups will be reflected into. And it's easy to see that these 2 groups are mirror images. And if you tried to superimpose those atoms on each other, you would never be successful. We need a way to name these compounds, showing the stereochemistry so that we can tell which is which. And a trio of chemists, mental giants in their fields, got together to devise a system for naming. It's called the Cahn-Ingold-Prelog system. The exact names of those individuals isn't important, but you may hear it because it's the universally accepted system for stating the stereochemistry, whether we have this configuration or that configuration of a stereoisomer. Here's the system. Number 1, number each of the groups attached to the carbon atom in their priority, assigning priority based on the weight of the atoms, the atom attached directly to the carbon. So in this case, for example, the heaviest atom is bromine, and the second heaviest atom attached to this carbon is fluorine, and the third heaviest atom is carbon, and finally bringing up the rear would be hydrogen, the lightest. The second thing this system says to do is orient the molecule so you're looking at it in a way that this lowest priority group is furthest away from us. Well, I wrote it that way. I wrote it that way for convenience, knowing I would need to. That 4th priority group is away from us. The third thing you do is, now forget the 4th priority group altogether and look at the first 3 and move in a direction that's clockwise or counterclockwise from 1 to 2 to 3. And if the direction is clockwise, then assign the stereochemistry as R. And that R is called the absolute configuration. It says absolute because that is not in reference to anything. But we can say what that configuration based on this assignment without knowing anything else about any other molecule. So it's the absolute configuration. Notice that word. It's easy to get this mixed up with conformation. This is configuration, and conformation is something we talked about earlier, where conformations are spatial arrangements that interconvert by bond rotation. These are configurations, and they do not interconvert. It would take bond breaking and bond making to interconvert them. And just to run a check to see that this is the stereoisomer, let's use the same system, and we'll number this as priority 1, priority 2, priority 3, priority 4. The 4th group is away from us. We will go from 1 to 2 to 3 in a circle, and we see that circle takes us in a counterclockwise direction, and so that absolute configuration is S. Let's take a look at the same molecule if we had written it differently and figure out how to get the configuration assignment correctly. Write this carbon. Let's just say that that hydrogen was pointing toward us instead of away, and the fluorine was back. We'll put the bromine and the methyl groups in the same places. We go ahead and assign the configuration with the hydrogen pointing toward us when it should be away. We'll do the 1, the 2, the 3. We see that we find ourselves going clockwise, and that would imply the R configuration. But we know that the hydrogen should be back. It's toward us. We need to change this. If the lowest priority group is toward us, the assignment will be incorrect, and the correct assignment must be the opposite. It's an S. What if we had this molecule and it was written in a very different way? Suppose this molecule were written so that the hydrogen were in the plane, and we have, let's say, the bromine also in the plane. We have a fluorine, and we have a methyl. Now how are we going to assign that configuration? Well, we can go ahead and number the groups, 1, 2, and 3, but we will have to write this viewed away from the hydrogen. So we will need to place our eye so we're sighting this way. And when we do that, we see that we can write this carbon atom in something that's like a Newman projection. And the bromine is sticking straight down. That methyl group is up and to our right, and that fluorine is up and to the left. And now the hydrogen, which needs to be oriented away from us, is. So then we can make our assignments. Bromine, fluorine, carbon, move from 1 to 2 to 3. This is clockwise, so the assignment is R. So you see that we can assign the configuration, whether the lowest priority group is away from us, as convention dictates, or toward us, in which case we'll get the wrong answer and change it, or in the plane, in which case we'll orient our eye to sight down a line that sees the carbon first and the lowest priority group after that. Now we need a word to describe pairs of stereoisomers that are mirror images that are non-superimposable. And that word that chemists use is enantiomers. Compounds that have all the atoms bonded to each other in the same order, but their mirror images are not superimposable. Their mirror images are not superimposable. They're stereoisomers of a special kind. They're called enantiomers. And we speak of them as a pair of enantiomers. And we can tell the two apart by giving them special names. The configuration, the absolute configuration, may be R or S, and we assign those terms based on the Cahn-Ingold-Prelog convention.